All right, so electric potential is a new concept that has no an analogous thing in gravitation or mechanics that we did before. So recall that from the previous lesson that the electric potential energy was the energy required to put together a specific charge configuration, right? If I had three charges, I got to put it together, and the potential energy is how much work it took to assemble those charges. Okay, if they were put them at infinite distance, I bring them together, that's the amount of energy it would take to how much work it would take to assemble those charges in that specific charge configuration. So the electric potential, so think about it like when you're assembling charges, it takes energy to assemble the charges. So if you want to move, let's say you have two positive charges, right? It takes an energy. There's an energy at this state, right? The potential energy. We'll call it mu naught. If I want to move this charge to here, there's going to be now a new energy. And so there's a change in the potential energy there, right? Because it takes energy to create a specific charge configuration at their distance. If I were to take one of the charges and move it, it's now going to take a different amount of energy. And that difference is the change in the potential energy of what's going on, right? And so the electric potential is related to that change in potential energy. It's considered to change in the potential energy between two locations, but the only thing about electric potential is that it's per unit charge, right? Because this change in potential energy is going to depend on both charges, but we're going to say hypothetically, if I were to take an imaginary charge from here to here, and I looked at that change in potential energy, the electric potential difference would be how much energy it took to move that charge per unit charge. Okay, it's a little bit confusing, but it is related. It's related to the change in the potential energy per that unit charge. So because work and energy are scalars, electric potential is a scalar quantity because it's related to potential energy. We're just dividing by the amount of charge. So let's kind of see how this works. Very similar to electric fields, we put that test charge. We're going to do a similar thing for electric potential. So the way we're going to handle this, or let's get into this. So recall from the work energy unit, work is the change in energy, right? So what you want to think about, and just to relate the potential in terms of energy, this is the easiest way to at least begin to think about it. Is imagine you put a positive test charge, just like we did for electric fields. We imagine that there's an external force would be necessary to move that test charge from one location to another, and this would take some work, right? And assuming we aren't changing the kinetic energy, all right, that work would cause a change in the potential energy. Okay, so that change in potential energy is equal to is done by work, and we say that's equal to Q test times this thing that we define here. This is we call the change in potential. Not potential energy. So potential is not the same as potential energy. It's just like the electric field was Q times the Q times the electric field gave you the force. Q times the change in potential would give you the change in the potential energy. Now, if you think of the potential as like we have a hypothetical test charge in there to think about that change in energy. So let's go through some examples, and that will help you begin to think about it. Potential is measured in volts. So that's the SI unit for it. You can think of it as joules per coulomb, right? Because if you do this delta V, you move it over here, you get change in potential energy divided by Q. The Q is measured in coulombs. This is measured in joules. Joules per coulomb is a volt, which we do denote with V, so volt like that. Okay, so let's think about it. So we'll go through some examples here in a second. So a single point charge would create potential at distance r away, V equals kq over r. Let's derive where that comes from. So let's say I had a positive charge. It's called q. It doesn't have to be a positive charge, but let's just say I have a place charge here. And let's place a q test. Okay, then we would say the potential energy, and it's a distance r away. The potential energy in this configuration would be just like k, it would be q times q test divided by r. Okay, now this is going to be Q test times the potential at that location. So you see, if we divide out the Q test, then we get the potential there to be KQ over R, which is dependent only on this charge. So when you have multiple point charges, the total electric potential would be the sum of the potential from each point charge. That's a scalar quantity, so it's easier to sum compared to electric fields. And now we'll go through some examples. Okay, So let's calculate the electric potential at point P from the other three charges in the configuration below. Okay, so if we think about this part here, let's imagine we put a Q test right here. So then let's think about the potential energy. So we're going to do it the long way, and then I'll show you the shortcut. The potential energy of the system, just like we did before, it's going to be 4 charges here, right? So it's going to be K, Q1, 1 in Q test over D. And we only want to think about the potential related to this charge, not the energy related for these charges. We're just talking about the potential for this charge. So it's going to be fewer pairs. Okay, KQ test times Q2 divided by D root 2, because the distance from here to here is D root 2. And then finally, you're going to have KQ test times Q3 over D, because from here to here is the distance D. Now, we're going to exclude the energy it took to confirm these guys, because we're really only talking about the energy related to bringing that Q test into this space. Okay, so we don't care about these parts because, again, remember, potential is about the change in energy, so we only are interested in the potential energy due to this extra charge here, because these guys aren't really going to change if we were to move the Q test around. Okay, and these, notice they all have Q test, so if we do UE over Q test, right, factor out the Q test, divide it, it's going to be KQ1 over D plus KQ2 over D root 2 plus KQ3 over D. And that gives you the potential energy of this. And that's simply, just like we did here, it's going to be KQ over R, but from these charges. So we're going to say at this location, this distance is D, KQ1 over D. That distance there is D root 2, so it's KQ2 over that. And then this charge is KQ3 over this distance D. Now, one thing that's nice about electric potential, more useful, because it's work in energy, it's a scalar quantity. That means, like when we had to add and find the net electric field there, it was trickier because we had to do it as a vector addition, right? We had to decompose into the X and Y components. But with electric potential, we only have to think about a scalar and we just add them up, KQ over D, which is really, really nice. And that makes it really, really nice. So if you were to ever ask about what is the change in potential, you're just saying, well, here's the potential at this location. What's the potential at a different location? So you could say, like, this is a potential at P. Let's call this location R. There's a potential at R, and the difference in the potential would be the voltage at R minus V at P. So we now know how to calculate the potential due to a particular charge, and then we're going to talk about the difference by saying, oh, what's the potential here minus what the potential here? We call that the potential difference. Okay, is the difference between 2 points in space. Okay, and again, it's related to potential energy. That's why we taught you how to calculate potential energy of a configuration, and now we're talking about the potential at a location, again, very closely related to the potential energy. Okay.